Let's look at the graph of the motion of the ball in the vertical direction only. So we're just considering how the ball moves in the vertical direction, and we're plotting it relative to time passing, right? And notice we left this with it left the person's hand with the exact same initial velocity that we said it had in our very first scenario, and the train car is going forward at the same velocity as it was in our second scenario. I'm going to set this in motion one more time so you can just concentrate on the ball and think about the path of that ball, and whether its plot should be the same or different from what it was when the car was perfectly stationary. Okay, I'm hoping that you're realizing that the fact that the car was moving down the track at 20 meters per second, if it was a constant speed, that doesn't affect the motion of the ball at all in the vertical dimension. This should match your experience. If you're standing and you're protected from the wind, and you're standing in some train or plane or bus or something going a constant speed in a straight line on a level track, or in a level path, then if you throw something upward, gravity still acts on it and just is pulling it straight downward to your perspective, and so the ball will spend the same amount of time in the air. It'll go just as high. If you launch it at the same speed upward, it'll go just as high and spend the same amount of time in the air, and will land right back straight down in your hand. Okay? So also, while the ball was going up and down, it was still in its motion. It was an object in motion, staying in motion in the horizontal direction. It already had 20 meters per second for a velocity before it was launched. It had 20 meters per second for a velocity after it was launched, and all the way through its travel upward and downward, it was still going forward 20 meters per second. So this plot should look exactly like our plot from the second scenario. It's a straight line with a tilt of 20 meters per second, with a slope of 20 meters per second, showing that the ball was going forward with the person and the train car as they all went down the track at 20 meters per second. And that's how the ball could fall right back down into the person's hand from the perspective of the person inside the train. All right, so let's set this all in motion, and we're gonna plot in blue. We're gonna plot the motion of the ball in the vertical, and in green the motion of the ball in the horizontal. And we've got two axes on the vertical this time. We have the displacement in the vertical direction, and on the other end you'll see we have the displacement in the horizontal. So we're plotting both of them on the same plot as time goes by. Okay, there you go. You can see your secondary vertical axis here labeled, and we went up to 70 meters there so that we could catch that very last little point, which is just beyond 60. Some of my plots haven't shown beyond 60 meters, so that's why you haven't seen that point on every single plot so far. Okay, notice I'm going to back that up and do it again. Track the ball with your eye this time. Notice it's going straight up and straight down. The scenery's going by at 20 meters per second. Okay, and notice since the scenery is going by at 20 meters per second, the ball is further down the track. In fact, if it was going 20 meters per second for 3 seconds, that means it should be a little over, and it's gone just a little bit longer, 3.06 seconds if I'm not mistaken. It should be a little over 60 meters further down the track than it was to begin with. So the person standing by the side of the track is actually going to see that sort of curved, arched path that we're seeing that is following the blue dot path. Okay, that's what the person by the side of the track is going to see. Now let's go back up and look at the third bullet here. It says, if the train were traveling at some other constant speed, would that change the path of the ball as viewed by the person on the train? Well, no, because if they're all going a constant speed, still the person on the train throws the ball straight up, and then to their perspective it comes straight back down into their hand. It was already going the speed of the train, the ball was, and when it's launched straight upward, it's still going the speed of the train forward, and until it comes back into the person's hand, at which time it's still going the speed of the train in the forward direction. But that path, as seen by the person standing beside the track, is going to change. Why is it going to change? Well, it's going to change because the train's either moving faster or slower. What does that do graphically for us? In the horizontal, it changes the slope of this plot. If it was going faster, we'd have a steeper plot, which means as time went by, the train car would be further and further down the track. For each second of time that went by, the train would have covered a larger distance down the track. Or if it was going slower, for each second that went by, the train would have covered a smaller distance down the track. So the arched path that the person standing beside the train would see for the ball, that arched path would either be more elongated if the train was traveling faster, or more crunched up and shortened if the train was going slower. But what about the maximum height the ball would reach? Same. What about the amount of time it would spend in the air from launch to catch? Same. So that wouldn't be changed. It's just that while the train is going down the track, if it's going at a different speed, it's going to get further or not as far down the track based on how fast it's going before the ball ends up back in the person's hand. Since the velocity in the forward direction is a constant velocity, as we mark time going by, there's a constant or consistent amount of horizontal displacement occurring. So as we mentioned before, for every second the train will have covered 20 meters. For every half second the train will have covered 10 meters. For every quarter second the train will have covered 5 meters. We could change out our units on the x-axis and put in displacement units, which this is not something we normally do, but it should help you understand why the ball, as viewed from someone outside the train, appears to have this arched path. 10 meters down the track means half a second later. 20 meters down the track means a full second later. 15 meters down the track means 3/4 of a second after the launch of the ball. So you can see that we can just substitute in regular increments of displacement for regular increments of time if the velocity in the horizontal is constant, and it is. Why is it constant? Why, after the person lets go of the ball, is the velocity in the horizontal constant? Well, gravity is not pulling the ball forward. Gravity is not pulling the ball backward. It only pulls the ball straight down. If the ball is launched straight up, gravity opposes that motion, and the ball will be affected by gravity only in the vertical. But in the horizontal, since there's no air resistance and since gravity has no effect in the horizontal, it's constant velocity. That's the nature of the motion of the ball in the horizontal. All right, let's put this in motion. Again, if you, with your eye, try to track the motion of the ball and not the motion of the graph, there you'll see that it's just going straight up and straight down from the perspective of the person inside the train. However, if you let your eye follow the graph, you'll see that the ball is taking that arched path. Got some take-home messages concerning projectile motion. These are the main points. If you can get these, projectile motion will be very decipherable for you. If we're talking about a different dimension, we're talking about independent motion. If we're talking about the vertical, we can treat that separately and independently from the horizontal. Or if we're talking about the horizontal, we can treat that separately and independently from the vertical. Again, we're usually trying to make simplifying assumptions, and one of our simplifying assumptions here is that there's no air resistance. If that's the case, then in the vertical component we'll have constant acceleration, and that constant acceleration is due to gravity. Gravity applies a constant force, and so there will be a constant acceleration of the object once it's launched and at the mercy of gravity. This only applies in the vertical component. In the horizontal component, which we can treat separately and independently from the vertical, the object will move with constant velocity. That constant velocity would be figured out from the initial conditions. So whatever the initial constant velocity is for the projectile, that's what it will be throughout the travel of the object if there's no air resistance. These are the major points. If you can get this one slide, if you can put it all together in your mind and refer back to it on each problem, this will help you solve these problems.